right, well, welcome everyone to this session on what's new and what's coming in Oracle Machine Learning, new features and roadmap. In this session, we're going to get an update on the new features in Oracle Machine Learning and look at what's coming this year. So I'm Mark Hornick with Oracle Machine Learning Product Management. Now this is Oracle's safe harbor statement since I'll be discussing the OML roadmap. So just by way of agenda, we'll start with a brief overview of OML components and OML's role in the Converged Oracle database. I'll then share items from our roadmap through 2022 and take a more detailed look at a few of these. About midway, though, I'm going to demonstrate the notebook highlighting expectation maximization clustering using OML for SQL. So let's get started with a quick review of the OML product family, just in case you're new to OML. So Oracle Machine Learning provides interfaces for machine learning in the database for three popular languages, SQL, R, and Python. Now, OML for SQL provides a SQL interface to the in-database parallelized algorithms, which allows us to keep data under database control and eliminates the need to extract data to separate machine learning engines, which is a key part of our value proposition. The resulting machine learning models are what we call first-class database objects, meaning that you can, for example, control access by granting and revoking permissions, audit user actions, and export and import machine learning models across databases. In-database models enable both batch and singleton scoring directly from SQL queries, which is great for developers who are already working with SQL most likely. In-database models also provide explanatory prediction details, so you can understand why an individual prediction was made. And we'll see an example of this in the demo. So OML for Py and OML for R are the Python and R language interfaces. And these allow you to manipulate database tables and views using familiar Python and R functions on data frame proxy objects. They also provide Python and R language interfaces to the in-database machine learning algorithms. OML for R and OML for Py also support embedded execution, where users can store user-defined functions in the database and invoke them through database-spawned and controlled Python and R engines. And in OML for Py, we have an API supporting automated machine learning, or AutoML. Now, for interaction with autonomous database, we provide OML notebooks with SQL and Python interpreters. Users can schedule notebooks to be run automatically, and notebooks can be shared in a variety of ways with other users on the data science team. Oracle Data Miner is a SQL developer extension for creating, scheduling, and deploying analytical workflows through a drag-and-drop user interface. Oracle Machine Learning for Spark provides machine learning on big data service with native scalable algorithms, as well as Spark MLlib algorithms included in the same framework, all from an R interface. Now, next is Oracle Machine Learning AutoML UI. It's a no-code user interface that automates model building, selection, and deployment. And finally, Oracle Machine Learning Services is a RESTful service for model deployment and model management, along with cognitive text analytics. OML Services supports application development using REST endpoints. Now note that users can deploy models from the AutoML UI directly to OML Services in just a few clicks. So with this as our basis, let's look at OML in the context of the Converged Oracle database. But before we do that, let's start with a poll. Which OML components have you tried so far? We're limited to 5 answers here in this interface, so hence the grouping. And Sherry just started the poll, so give us a sense of, which of the components have you worked with so far? That's looking pretty good. And we've got 76, 78, 79% for the programming interfaces. OML notebooks, about 3/4 of the folks, and then others coming in with the AutoML UI at 50%. So that's really nice to see. All right, so that gives us a basis of what folks are doing. And let's continue with the Converged database strategy. So I suspect that you've all heard of Oracle's Converged database strategy. We know that crafting a solution involving multiple single-purpose databases suffers from increased complexity in component interactions and growing integration and maintenance costs. Further, end-to-end security, availability, and scalability can be inconsistent and worse, limited by the weakest of the multiple single-purpose databases used in a solution. Oracle's Converged database eliminates these issues for a wide range of technologies, supporting multiple data types and workloads, including those for machine learning. Now, having Oracle Autonomous Database as a data science platform involves more than just supporting machine learning algorithms. Oracle's Converged database places machine learning and other essential technologies, like, of course, query processing, but also spatial, graph, JSON, blockchain, and others at the fingertips of data professionals, especially data scientists. All of this is in a single, secure, integrated platform while expanding data access and sharing for all data professionals. Further, these converged technologies are included in the core database at no additional cost. So with that, here's a high-level summary of 2021 OML releases and a sample of features we have planned through 2022. So after releasing OML for Pi, OML Services, and the OML AutoML UI for Autonomous Database earlier last year, we released OML for Pi for Oracle Database 21c, which includes on-premises and database cloud service databases. In response to customer feedback, last December, we enabled features of Oracle Data Miner on Autonomous Database, giving users access to the no-code drag-and-drop user interface to data that's stored in Autonomous Database. For new Autonomous Database instances, the OML Notebooks repository is now in the user's Autonomous Database instance. And this is important because it enables database instance-specific backup and restore of notebooks, as well as cross-region Autonomous Data Guard features. And this same feature will be enabled for existing Autonomous Database instances in the next month or so. We're just going to be rolling out a migration plan for that. Now, coming soon, we'll be releasing OML for Pi for on-premises Oracle Database 19c, along with a standalone, what we're calling a universal client. And I'll say more about that later. On Autonomous Database, we're supplementing the embedded Python execution REST API with a corresponding SQL API. Recall that embedded execution allows running user-defined Python functions in database-spawned and managed Python engines. And we'll see a code example of this shortly. Now, later this year, we're updating OML for R151 to be compatible with R405 for Oracle Database. And we'll be releasing a new Oracle R distribution in support of R405 as well. On Autonomous Database, we plan to add the ability to load third-party Python packages for use with OML for Pi's embedded Python execution and OML notebooks. This is a much requested feature. Third-party package support is already available for OML for Pi on Oracle Database and Database Cloud Service. And this feature will allow users to leverage the broader Python package ecosystem with Autonomous Database. OML for Pi will also be enhanced to support date-time data types, initially on Autonomous Database, and then introduced for on-premises and DBCS databases as well. In OML Services, we're adding support for in-database batch scoring, so you can use the same REST API as for singleton and small batch scoring, doing this at scale in the database. Also, we'll be adding an R interpreter to OML notebooks in support of OML for R to further enable Autonomous Database as a data science platform. We also plan a new monitoring interface on Autonomous Database for data and model drift detection. And I'll give an illustrative example of what we have planned toward the end of today's session. Now, coming later in 2022, our plans include augmenting OML for Pi in a number of ways. For example, to programmatically deploy in-database models to OML services, have APIs for 21c algorithms like XGBoost. And there will even be some transparency layer enhancements for data preparation and statistical methods. In the AutoML user interface, we're adding the ability to schedule experiments. And this supports automatically rebuilding models using the same jobs interface that we have for OML notebooks. We'll also be augmenting AutoML to support anomaly detection, in addition to the currently supported classification and regression techniques. Now, not listed here, but equally important, are multiple Oracle Database 23C enhancements. We're going to save that for another office hours session. But meanwhile, there's also ongoing integration efforts with Oracle Analytics Cloud, Oracle Data Integrator, OCI Data Catalog, and OCI Data Science. And all of these are important for a well-integrated environment for data science projects. So we're looking forward to bringing those online. Now, since we can roll out enhancements to cloud services more frequently, here's a summary of a few of the more recent enhancements, some of which Sherry covered in our December 7th office hours session. I'll briefly review some of these here as a refresher. So in OML Services, we now support ONIX format clustering models and cognitive text analytics for the Italian language, which adds to the languages already supported, English, Spanish, and French. We're considering additional languages and scheduling them as resources and demand dictates. For Jupyter users, you can now also export your notebooks in Jupyter format from the notebook listing page. Since last year, you could already import Jupyter notebooks. We've also expanded the set of example notebooks to cover the range of in-database algorithms and OML for SQL and OML for Pi. Oracle Data Miner is now compatible with Autonomous Database, as I mentioned, and you can see the recent blog post and the January 11th office hours sessions for details on setting this up. Sherry did a great job of highlighting how we accomplished that. We've updated the pre-built explicit semantic analysis Wikipedia-based model, supporting capabilities like text feature extraction and text similarity. And this explicit semantic analysis wiki model is built using millions of Wikipedia articles with the topics reduced to about 160,000. And you can download the model from the link shown here. As we've discussed and demonstrated in previous office hours sessions, we've simplified the URL structure for OML for Pi, OML Services, notebooks, and the AutoML UI. For example, with OML Services, we no longer need the tenancy OSID or database name when invoking OML Services endpoints. And with OML AutoML UI, we've turned on producing model details by default, and this allows users to better understand the models produced by AutoML. So let's look at a few of these in more detail. First, OML Services. OML Services on Autonomous Database supports lightweight model scoring using REST endpoints for application integration. Now, by lightweight, we mean that OML Services optimizes scoring performance for streaming and real-time applications. OML Services provides model management and deployment for in-database and ONIX format models using REST endpoints. Now, since it's included with Autonomous Database, no explicit VM provisioning is required for 24/7 availability. The Autonomous Database environment entirely manages the compute resources. Further, users just pay for the additional compute when producing actual predictions. Users can deploy in-database models from Autonomous Database to OML Services, but they can also deploy models that were developed using on-premises and DBCS databases as well. So when it comes to deploying third-party ONIX format models, users can build machine learning models outside the database environment, for example, using Python in OCI Data Science or another Python environment, or even an R environment. Using the REST interface, users can import these models to OML Services for use by enterprise applications. By the way, ONIX, it stands for the Open Neural Network Exchange. It's an open format for representing machine learning models. But it's more than just neural networks, unlike the name implies, obviously. Now, OML Services supports machine learning techniques for classification, both image and non-image models, a regression, and the recent addition of clustering models. So let's look at an example involving a third-party clustering model. Once we have a clustering model, say in the variable class that we produced in our Python interface, we export it in ONIX format. And this shows invoking to ONIX on the class model, and then invoking the ONIX ML tools save model to get the .onix file and the corresponding metadata. Finally, we write the zip file that includes both the JSON metadata file and the ONIX file. To deploy this model to OML services, we first get an authorization token, as shown here using curl. Note that we're using the simplified URL format without the tenancy OSID or the database name. Then in the second curl command, we store the model by passing the model's name and version, that the model type is ONNX, and whether this is a shared model. We also specify the zip file that contains the ONNX format model and metadata. Optionally, we can specify a name for organizing models into groups. So once stored, the model can be used for real-time scoring in applications and dashboards as a REST endpoint. And here we invoke the score endpoint with a model plus ONNX 5. You see the input record provided there for the data that will be used for scoring. So on to OML notebooks. We already mentioned that for new autonomous database instances, the OML notebooks repository is now in the user's autonomous database instance, which enables database instance-specific backup and restore of notebooks, as well as cross-region autonomous data guard features. You might know that Oracle Data Guard ensures high availability, data protection, and disaster recovery for enterprise data. Regarding OML notebooks itself, I'll just highlight that we've provided example notebooks that cover the full range of algorithms supported by OML for Pi and OML for SQL, along with the new 21C algorithms for XGBoost and MSET for anomaly detection. You can also see an example of how to load data into your autonomous database instance where the data is stored in GitHub. Many of the notebooks have been augmented to include descriptions of the settings available for specific algorithms, but I still recommend you check out the documentation for the full range of settings that are available. And even with these additions, we're in the process of updating the example notebooks for 2022, and we'll be adding a few new ones there as well. For example, you'll get to see how do you import wide data sets, such as CSV files with more than 1,000 columns. This example uses a combination of OML for Pi, embedded execution, followed by SQL for constructing the nested column. Another notebook will be introduced to show using OML for SQL to build models using these nested columns. We'll also be adding a notebook that provides a more generic PL/SQL procedure for programmatically importing data into autonomous database from object storage. So here's the full set of notebooks currently available with the 2021 editions highlighted in red. And you can find these in your autonomous database instance by clicking examples on the OML homepage. Okay, so one of our requests we had through the office hours feedback was to show more of the OML for SQL API. So let's look at an example using the in-database expectation maximization algorithm for clustering. In our January 11th office hours session, Marcos demonstrated using OML for Pi for k-means clustering in some detail and briefly looked at the SQL API for EM. So we'll look at this EM notebook in more detail here. So this is the notebook that we've revised for 2022, so you're getting a preview of this. But essentially, we start off with the settings for the interpreter binding, and we're going to be using the medium settings, so we get some parallelism involved when we're doing the machine learning. In the notebook, you'll see that we have documentation links that you can access. So if you'd like to understand what is expectation maximization about, you can read all about it. Also, there are some generic settings as well as detailed settings for the EM algorithm in particular. And all of the algorithms have this type of documentation available. So when we go to use the notebook environment, one of the first things we'll do is access the data that we want to use. And in this case, we're going to create a view, a customers 360V, which is joined between customers and supplementary demographics from the SH schema. Of course, we can then look at some of the details of the data, how many records we have, and what are some of the values that are available. But the main focus here is how do we build models doing this? And what is the SQL API for Oracle Machine Learning? What does it look like? So we're going to build an EM model here with default settings. So minimally what we do is if we have a model that's already named that, we'll drop that because it will give us an exception if we try to build a model with the same name. So we're going to drop that first. Then we're going to create a settings list here in our PL/SQL block. The only thing that we need to specify in this settings list is the algorithm name. And in this case, you see that it's expectation maximization. The main procedure that we're going to invoke here is create model 2. And it takes the model name that we want to use, the fact that this is a clustering technique. The data query, in this case, this could be arbitrarily complex, but here we're just selecting all the data from customer 360V. The settings list, so this is the object that we created up here, and a case ID, which is the unique identifier for each row. And this can be optionally specified and can also help with repeatability for building the model subsequently. Now, as I mentioned, some of the notebooks have included examples of what the settings are right there, so you don't have to go off to documentation. But here you see there are links for the algorithm settings, the shared settings, as well as the specific ones for EM. And the more common ones are included right here in this notebook. But let's go on with how do we use these settings. So this is essentially the same example from before with a few additions. We're adding settings for automatic data preparation. By default, it is on. We're showing here that this is how you might turn it on or off in this case. How many clusters do we want? The default is 10. Here we're overriding it with 5. And there are a number of other settings that we can include as well. Invoking create model 2, we're going to just change the name, incrementing it to sample 2, but everything else remains the same. Now, once we build this model, we can display the model metadata. And with this, we're going to use the user mining models table that's available. And this is essentially the in-database repository for the first-class model objects that exist in the database. And here we see, if we're looking for all of our EM type models for this demonstration, we have 3 of them, 1, 2, and 3. And we've built 1, we have 2 that we just built here, and 3 is coming a little bit later. But you can see the mining function, the algorithm that created it, and then the creation date, as well as whether or not the model is partitioned. In case you're not familiar with partitioned model, this is a way that we create an ensemble of models where the system will automatically build multiple submodels for you based on partitions of the data specified by 1 or more columns. What you get back, though, is a single model that you can use for scoring. And behind the scenes, we'll identify the specific submodel that needs to be invoked based on the partition that is appropriate for it. So that's what partition model is. Now then, we can look at what is the model signature for our EM model. And in this case, we're going to use the table user mining model attributes. So we see the attribute name and its type, and this just highlights what were the attributes that were used when training the model. From there, we can display the actual settings that were used by the algorithm. Notice that we didn't specify all the possible settings, and so the algorithm is going to either use default values or intelligently select certain values that might be best suited for the data. And so we're using user mining model settings and selecting our particular model and getting back the settings name and settings value in this case. Here we see again, we asked for 5 clusters, we're getting that. We have the cluster components is enabled, cluster statistics is enabled, as well as various settings for those that we didn't specify, but we get a complete accounting of what was used in building this model. Now, all of the in-database models have what are referred to as model detail views. And these are all prefixed with a $V and a letter. That is then followed by the name of the model itself. So in this case, in our EM model, we have EM/SH clus sample 2, and the prefix here is going to get us to things such as what are the clustering attribute statistics or the clustering description, maybe the clustering histogram. So let's look at a few of these. We can show the cluster details here with the $VDEM/SH clus sample 2 view. We see for each cluster ID, what's the record count, what is its parent, because this is a hierarchical clustering model, and its level in the tree. We can also show leaf clusters IDs, which are the leaves in our tree, and we do that simply by filtering out those that have no children associated with them. We wanted to look at the cluster details for a particular cluster, in this case, cluster 9. We see that for the cluster ID, these are the various attributes and what the mean, variance, and mode for those corresponding attributes are, depending on the data type. We might also want to compare the histogram for certain attributes to compare clusters, right? So in this case, we're looking at years residence and showing the distribution for cluster 6 versus that for cluster 9. Notice that we're selecting the cluster ID, the attribute name, from the $VH model detail view and filtering for years residence, and in this case, cluster 6. We're using the visualization native to Zeppelin to support this, obviously. If we wanted to, we could look at the specific bin boundaries for year residence and see what is the lower and upper bound as well as the count that's in there. And this is what we used, obviously, for producing the histograms up above. Going a bit further, we can display the rule details for a leaf cluster if we wanted. And in this case, we're going to see that for cluster 3, we have the various attribute names and the operators, numeric values, and the support and confidence that supports each of these rules, if you will, that define what are the boundaries for each of the cluster definitions. Now, you might say this is good to have this level of detail, but it's not necessarily the most convenient way to look at that. And for that, we're going to jump to Oracle Data Miner for a moment. That will allow us to look at some model details with viewers specific to Oracle Data Miner. Now, if you're not familiar with Oracle Data Miner, I'm going to talk a little bit more about that later. The main thing I want to highlight is that we have the ability to create nodes in this, and we can select models that we want, and we can look at the models that are in Autonomous Database, right? I've created these models in Autonomous Database. And perhaps I want to select our sample 1, and I'm just going to close that. Now I can right-click and say View Models, and we see EM/SH Clus Sample 1, and this is going to give us a viewer for that model in the database. So we can now visualize the tree of the various nodes for our clustering model. We could start at the top if we wanted, but normally we might go to a leaf cluster, and we can get the details of, well, what is the centroid and what is the relative importance of each of these attributes in that centroid. We have the mode, the mean, the variance, and support reported here as well. Now, we were looking at the rules earlier, and this gives you a very convenient way to understand what is the rule definition for that particular cluster, along with the confidence and support. And since this is an EM model and is composed of, potentially multiple components, we see what are the components that are supporting this particular cluster. In this case, we're looking at a particular cluster here for cluster 9. Now, we can also look at some of the details for the cluster itself. So this is the distribution of values for each of the predictors for a cluster. In this case, we're looking at cluster 3. We can also compare clusters and other features as well. So I hope this gives an idea as to what we can do in this environment. So going back to our notebook environment, we might want to determine how many customers are in each of the clusters. And so again, we're going to select the cluster ID. We're doing this dynamically, notice. We're invoking the model to get the cluster ID on the data customers 360V, and this is being computed dynamically. So if anything changed in the underlying table data, we're going to see that result dynamically. And this is one of the nice aspects of working with the in-database machine learning algorithms on table data, because if you do have sort of a dynamic backend, you can get the scores that are most current on that data. And we're just highlighting that here. To continue on, maybe we want to list the customers most likely in cluster 6. Again, we're doing this using SQL queries. And I had talked about this notion of what are the prediction details, why a given prediction was made. And this is a query that uses our model, the EM/SH Clus Sample 2, to get the scores, but to actually pull out what are the attributes that are contributing most to the prediction. So we see with customer ID here, 362, the cluster ID is 8, 100% probability, and we see that the year of birth is one that is the most influential, followed by whether or not they purchased Y-Box games. Now, there are some alternatives to building clustering models as well in the SQL interface. So we just highlighted how you can use PL SQL blocks to do that. And here's one where we can build a clustering model on the fly, so to speak, where we are saying we want to get the cluster ID, and we want to have 4 clusters identified using these predictors. And this query then is going to dynamically build the model and give us access to the cluster ID as well as the cluster details just as we have above, but we're not storing a model in the database for later access. And this just is a very dynamic way of generating this content. And again, you see the customer ID, the corresponding cluster ID, and then the first, second, and third attributes there. But there's still another way that you can build clustering models, and this one uses a settings table. So it's an alternative that allows us to store the settings in an explicit table. And this can be beneficial, certainly if you want to reuse the same table and have different settings, perhaps dynamically from some interface where the user is selecting those settings, but you don't want to have to revise the code that does that. All the settings can be changed just in the table. So it gives you another level of flexibility in that. So what we're doing is creating a table called EMSH sample settings. First, we're going to delete any table that might have existed before. And then we'll also prepare by dropping the model because we're going to build yet a third model. But in the settings table, we're going to say, yes, we want the EM algorithm. We want to enable search. We want data preparation to be turned on, which is on by default, by the way, and the plus stats to be enabled as well. And from here, we can look at what does our table contain, the settings table, exactly what we specified. These are the rows that we inserted, and then we'll build the model. So notice here we're using a different procedure. Earlier, we used create model 2, and that allows us to purely use the PL SQL to specify all of the settings. Using create model, very similar, but some differences you'll notice we have a data table name where we're specifying, in this case, the view that we want to work with, and the settings table name. In this case, the EMSH sample settings that we just viewed over here on the left. And after building that, just as before, we can see what were the actual settings that were used in constructing this model. And that's available in the same user mining model settings table that we looked at earlier. And all of the other features I talked about are also available to you there. So I hope that gives you a good idea as to what the SQL API is about in several different ways. The create model 2, the dynamic creation of clustering models, and the like. So with that, let's continue on, and I'll just make a few more comments on Oracle Data Miner. So I'm sure that some of you have worked with Oracle Data Miner. Some of you indicated that on our poll earlier. So just to summarize, Oracle Data Miner is a SQL developer extension, right, as you've seen, that supports creating analytical workflows, serving as a productivity tool for data scientists and enabling citizen data scientists with a code-free environment that automates many common machine learning tasks, such as data preparation, model building, and model evaluation. Oracle Data Miner provides this functionality through a drag and drop interface where users connect nodes to construct analytical workflows. And you'll notice a palette of tools on the right in this screen capture for tasks such as data access, exploration, and transformations, and integrated text analysis where data columns can be identified as text for automated TF-IDF tokenization, among other settings. Now, there are nodes supporting model building for various machine learning techniques, as well as accessing model details, as we've seen. You can also score data and evaluate models. Users can also schedule workflows to run on a set schedule, which supports periodically refreshing models or generating batch scores. Oracle Data Miner has always been compatible with Oracle Database on-premises and Database Cloud Service, and now is available for autonomous database users as well, as we demonstrated in this last example. So let's move on to the coming soon OML for Pi Universal Client and Oracle Database 19c support. OML for Pi was introduced on premises for the 21c innovation release. However, with many customers using the long-term 19c release, we'll be making OML for Pi available on 19c there as well. The OML for Pi Universal Client allows a standalone Python engine on Linux to connect to supported database versions of both 19C and 21C for Autonomous Database and Oracle Database. So one package can be used to access each of these. Of course, this is important for users who want to work with OML for Pi on Autonomous Database, but also take advantage of third-party IDEs and other notebook environments like JupyterLab. It further allows switching between on-premises and Autonomous Database instances using the same client package. Users can connect in a variety of ways using the oml.connect function, either through explicit user and password or using an Oracle wallet. And if you're not familiar with the wallet concept, an Oracle wallet is a secure software container that stores authentication and signing credentials for an Oracle database. So you don't have to use clear text passwords in your code. And later this year, the OML for Pi client package will be made available on OCI Data Science, so you can get in-database scalability from that environment as well. So next is the SQL interface for OML for Pi on Autonomous Database. Here's an example showing OML for Pi SQL interface for embedded Python execution. Now on the left, we have user-defined Python function that builds a linear model from scikit-learn, then saves this model in the database using the data store. And these are basic concepts for OML for Pi, which we've covered in past sessions, and certainly in the hands-on labs with the live labs that we have available for OML for Pi. And so this returns the model string. This function is stored in the Python script repository in the database using the PyQ script create function under the name myLinearRegressionModel. So you can not only create scripts in the script repository using the Python API, but you can also do this from the SQL API, which makes it very convenient as everything you're doing is from SQL. On the right, we show invoking this Python function from SQL using the table apply functionality and the PyQ table eval table function. The system automatically populates the first argument dat of the user's function with data from a database table, and this provides a pandas data frame to your function. We pass in the iris table name, the user-defined function parameter list, which includes the model name and the data store name. And we specify the output format as XML and the name of the function as stored in the Python script repository. Running this select statement results in a Python engine being automatically spawned, the function loaded, and the table data loaded as a pandas data frame in the argument dat. So when it's finished, you have a native Python model stored in the database that's ready to be used by another embedded execution invocation, such as row apply, which enables the use of system-supported data parallelism. Now, on the bottom right, we see the output after invoking the function, which is simply the value returned from str that we invoked on the model, and it has the value linear regression provided as an XML string. The last item I'll touch on is a new feature called OML Monitoring. The latter part of solution deployment involves data and model monitoring. And this is where users can be alerted when data drift or model drift have occurred. In case you're wondering, data drift involves identifying significant changes in the statistical properties of the data, which may indicate the need to rebuild a model. Essentially, we start with some baseline data and compute an initial drift metric. And later, we evaluate new data to see if the computed metric surpasses our alert threshold. When new data is shown to deviate significantly, an alert is recorded. And this informs the user that rebuilding the model is likely warranted. Similarly, model drift includes observing if the model accuracy metric is degrading over time, again suggesting that rebuilding the model may be warranted along with possibly investigating root causes. So like data monitoring, users provide new test data sets periodically to evaluate the model accuracy metric. And some user scenarios may include building multiple models using, for example, different algorithms or settings. And these models then compete based on their accuracy metric. So this champion score, if you will, can guide which model should be used by the application. And when the metric goes below a defined alert threshold, this fact is recorded so users can decide if the model should be rebuilt. And in the first release, OML Monitoring will support in-database models, and later will include ONNX format models.
Hey, Mark?
Yes.
So there's a question, I think it goes very well with what you're showing, which is any thoughts about machine learning ops using OML and ADW?
From the MLOps side, I mean, there's a lot that goes into that. That's really an excellent question because Oracle Machine Learning supports MLOps from the deployment standpoint and the managing of your models. There's an entire sequence of functionality that encompasses the MLOps strategy. But for this question, I'll just say that we have the models in the database that allow you to deploy them immediately and have access to them, and you can back them up, you can export them, put them across different environments, so you can export your models from one environment, say a dev, into a production environment. And so all of this is in support of the overall MLOps strategy. Now there's more to that, and model monitoring is a key element of that. And that's one of the reasons why we're introducing this feature in 2022 to further round out what we're offering in the area of MLOps. All right. So that brings us to poll question number 2. And this focuses on Oracle Machine Learning for Python. Which of the new OML for Py features are you most interested to see released? Is it the Universal Client? Is it the Oracle Database 19c on premises? Embedded Python execution with the SQL API, as we saw, installing third-party packages on autonomous database, or date time support. And so we see everybody wanted to have 19c, the third-party packages, the embedded Python SQL API is fairly high there as well. All right, this is very good to see that we've got 19c is going to be a very welcome feature for that. So thank you for responding to that poll. And before closing, I'd like to call your attention to a few OML resources. You know, our blogs can be located using the bit.ly link provided here. And one of our recent blog posts discusses the top 10 reasons to use machine learning in Oracle Database. So I'd be interested in any feedback you have. Do you agree that those are the top 10, or are there others that you feel would be even more appropriate to highlight? Now, for additional SQL, Python, and R code and notebook examples, you can check out our GitHub repository. And of course, see our library of recorded OML office hour sessions. There's also a new OML on Autonomous Database Specialist certification available. And so I would encourage you to take that certification and add it to your skills. In support of this certification is a new set of Oracle Learning subscription content specific for OML, which can help you prepare. We've updated the OML for Py workshop in Live Labs and released a new workshop, OML Fundamentals, that highlights our autonomous database-centric components. So to see our recorded sessions from last fall's Oracle Database World, check out this blog post that's listed here. And lastly, consider joining our Oracle Machine Learning LinkedIn group. So thank you for joining us for this session. And if there are any additional questions, I'm happy to take them now.
So there is one more in there, Mark. Do we have all models, including XGBoost, supported by Data Miner?
That's a very good question. Oracle Data Miner has algorithms, I believe it's up to 12.2. The more recent algorithms have not been added. And we'll have to see if we include that going forward. That's not currently on our roadmap, but certainly there has been interest in that. We will be extending the OML for Py and R interfaces to have the 21c algorithms that are there.
There's another one here. Another question is, can we get the dr $VM views available in database for all classification and regression algorithms or for specific algorithms?
The views that are there are different ones that are appropriate for specific algorithms. And so I would refer you to the documentation where it highlights what views are available for which algorithms. And also the query that I showed, you basically invoke it on the particular algorithm, and it will tell you exactly what views are available with a description of what features are there.
So there's one other one here. Where can we find the list of machine learning features available for on-premise database? it seems like the now focus is on cloud and not on-prem.
Well, certainly we have a cloud-first strategy, so we want to make sure that new features that are brought out are appearing first with our autonomous database offering. Once available on autonomous database, some features will be made available, as we have with Oracle Machine Learning for Python for our on-premises customers' users. Similarly, the features that we've had on premises for a long time are being brought forward to the autonomous database environment. So Oracle Data Miner, that was exclusively on premises in DBCS, and just this past December, we added that for autonomous database. And OML for R is another one that we've had since about 2011 for on-premises databases, and now we're going to be augmenting autonomous database for that. So there's this back and forth depending on sort of customer demand, as well as available resources as to which features that we have on autonomous database will be brought elsewhere. One of the questions we often get is, are the autonomous database interfaces such as the AutoML UI, OML notebooks, even OML services, are they going to be made available on premises? And there's some discussion about how that might be enabled for things like autonomous database cloud at customer. And that's one that we're looking at, and you might see that on our roadmap going forward. Well, thank you all again for joining us, and until next time, have a great week.